Welcome to the new section of this course, Lambda expressions. Now let's move on to the video experimenting with functions using lambda expressions. Let's start with defining functions on the run using lambda expressions. Let's take a look at the code example. Let's understand our code. Here we will type a little program in which we play with lambda expressions in order to get a feeling for them. Let's understand the code. Lambda expressions do not need any library support, but we are going to type messages to the terminal and use strings, so we need the headers for this. Everything happens in the main function this time. We define two function objects that take no parameters and return integer constants with the values 1 and 2. Note that the return statement is surrounded by curly brackets like it is in normal functions, and the parentheses which denote a parameter-less function. These are optional, we don't provide them in the second lambda expression, but the square brackets have to be there. Now we can call both the function objects just by defining the names of the variables they are saved to and appending the parentheses. In this single line, they are indistinguishable from normal functions for the viewer. Next, let's forget about those and define another function object, which is called plus, because it takes two parameters and returns their sum. This is also easy to use, just like any other binary function. As we defined its parameters to be of the auto type, it will work with anything that defines the plus operator, just as strings do. We do not need to store a lambda expression in a variable in order to use it. We can also define it in place, and then type the parameters in parentheses just behind it, as I have highlighted here for your reference. Next, we will define a closure that carries an integer counter value around with it. Whenever we call it, it increments its counter value and returns the new value. In order to tell it that it has an internal counter variable, we type count equal to 0 within the brackets to tell it that there is a variable count initialized to the integer value 0. In order to allow it to modify its own captured variables, we use the mutable keyword, as the compiler would not allow it otherwise, and then you can see we increment the counter value. Now let's call the function object 5 times and print the values it returns, so we can see the increasing number values later. We can also take existing variables and capture them by reference instead of giving a closure to its own value copy. This way the captured variable can be incremented by the closure, but it is still accessible outside. In order to do so, we type &a between the brackets, where the ampersand means that we store only a reference to the variable, not a copy, and here we increment a. If this works, then we should be able to call this function object multiple times and then observe that it has really changed the value of variable a. The example that we saw is currying. Currying means that we take a function that can accept some parameters and store it in another function object, which accepts fewer parameters. In this case, we store the plus function and only accept one parameter, which we forward to the plus function. Here we forward x to the forward function. The other parameter is the value 10, which we save in the function object. This way we get a function, which we call plus 10, because it can add that value to the single parameter it accepts. You can see we have provided value 5. So it's time to compile and execute our code. Before compiling and running the program, go through the code again and try to foresee what it will print to the terminal. Then run it and check against the real output. Go to your terminal and type in the command for compiling the code. After the successful compilation, let's execute it. Nice! Here is the desired output. We get value of a after 3 incrementer calls. Now we will be adding polymorphy by wrapping lambdas into standard function. Let's take a look at the code example. So go to the Atom editor, then click on the ex2 directory, and inside that, click on the std function.cpp file. This is the entire code. Here we are going to create several lambda expressions that are completely different in regard to the variable types they capture, but have the same function call signature in common. These will be saved in one vector using the standard function. So let's understand the code. First, do some necessary includes. We implement a little function that returns a lambda expression. It accepts a container and returns a function object that captures that container by reference. The function object itself accepts an integer parameter. Whenever that function object is fed with an integer, it will append that integer to the container it captures. You can see another little helper function will print whatever container instance we provide as a parameter. In the main function, we've first instantiated dq, a list, and a vector, which all store integers. Now we use the consumer function with our container instances d, l, and v. We produce consumer function objects for those and store them all in a vector instance. Then we have a vector that stores 3 function objects. These function objects each capture a reference to one of the container objects. These container objects are of completely different types, and so are the function objects. Nevertheless, the vector holds instances of standard function. All the function objects are implicitly wrapped into such function objects, which are then stored in the vector. Now we feed 10 integer values to all the data structures by looping over the values and then looping over the consumer function objects, which we call with those values. All 3 containers will contain the same 10 number values. Let's print their content. So let's compile and execute our code. Go to your terminal and navigate to the ex2 directory. Next, we will clear the screen using the reset command. After that, type in the command for compiling the code. After the successful compilation, let's execute it. Superb! We have got the output we expected. Now we will be composing functions by concatenation by imitating function concatenation in C++ with Lambda expressions. Let's take a look at the code example. So go to the Atom editor, then click on the ex3 directory, and inside that, click on the concatenation.cpp file. This is the entire code. Here we will be defining some simple toy function objects and concatenate them, so we get a single function that applies the simple toy functions after each other to the input we give it. In order to do so, we will start by creating our own concatenation helper function. Now let's understand our code. So first we need some includes. Then we implement the helper function, concat, which arbitrarily takes many parameters. These parameters will be functions such as f, g, and h, and the result will be another function object that applies f of g of h on any input. Now it gets a little complicated. When the user provides functions f, g, and h, we will evaluate this to f of concat of g, h, which again expands to f of g of concat h, where the recursion aborts, so we get f of g of h and so on. This chain of function calls representing the concatenation of these user functions is captured by a Lambda expression, which can later take some parameters p and then forward them to f of g of h of p. This Lambda expression is what we return. The if-const-expression construct checks whether we are in a recursion step with more than one function to concatenate left. The other branch of the if-const-expression construct is selected by the compiler if we are at the end of the recursion. In such a case, we just return the function t because it is the only parameter left. Now let's use our cool new function concatenation helper with some functions we want to see concatenated. Let's begin with our main function, where we define 2 cheap simple function objects named twice and thrice. Next, let's concatenate. We concatenate our 2 multiplier function objects with the stl function, which takes 2 parameters and simply returns their sum. This way, we get a function that does twice of thrice of plus of a and b. After that, let's use it. The combined function looks like a single normal function now, and the compiler is also able to concatenate those functions without any unnecessary overhead. So let's compile and execute our code and check what output we get. Go to your terminal and navigate to the directory ex3. Next, we will clear the screen using the reset command. After that, type in the command for compiling the code. After the successful compilation, let's execute it. Nice! We get the output as 30, which we also expected as 2 into 3 into in bracket 2 plus 3 should ultimately give the output as 30. So here we have come to the end of this video. In the next video, we will be playing around with logical expressions.